Welcome back, friends. Now let's start with power electronics switching. How to switch AC and power load by using microcontroller. This can be done in two ways: electromagnetic relay switching or static switching. Due to long life, efficient, silent and reliable operation, static switching is preferred over electromagnetic relay, even though it is expensive. Here my discussion is concerned only with static switching, that is, power semiconductor switching. As I had said earlier, power electronics, the most dominating technology of this century, a link between computer and real-life application, that is, electrical system, widely used in almost all the electrical system of today, either it be power transmission in the name of facts, motor control in the name of electric drive. Today, even inside advanced electric machine, power electronic circuit are used for better commutation and efficient operation. Let's start to build our own switching circuit. Here is the mind map to do so. First, we must select our power switching device. Then we must create an isolation between Arduino and power circuit. And finally, we must connect circuit and load. Start with power switching device selection. There are a lot of power semiconductor switches, broadly classified into three categories: diode, thyristor, and transistor. Diode is of no use here as it is uncontrolled turn on and turn off. Thyristor. There are many types of thyristor like SCR, that is silicon control rectifier, TRIAC, GTO, gate turn off thyristor, and even there are many kinds of transistor like power BJT, power MOSFET, IGBT, and many more. But out of these devices, which one should be used in our circuit? This is decided by the characteristic required by our circuit. Here is the desired characteristic. The power semiconductor switch must have pulsating gate requirements, not a continuous gate, as the continuous gate causes unnecessary losses. It must be controlled turn on, so this is crossed here as it is uncontrolled turn on and turn off, and these two are still valid. And bipolar voltage, yeah, again these two are valid. Many type of thyristor had capability to withstand bipolar voltage and low cost. And low cost never comes for free. It comes at a cost of low switching frequency. So now let's see. TRIAC is best suited. But why? Because of its low cost. Low cost never comes up free. It always costs something. Here it costs low switching frequency. Let's see a graph between device VI rating and switching frequency. TRIAC. Here as we see, TRIAC has got a low switching frequency and available at low VI rating, while thyristor with low switching frequency are available at very high VI rating. They are available at the rating of thousands of volt and thousands of ampere. And the power MOSFET, they are available at very high switching frequency but at average VI rating. And even power MOSFET are costly. What we need here, what is the demand of our circuit here? We need to switch on and off power load by using remote control, and the remote control is to be operated by human, and human can't operate at frequency greater than 10 raised to the power 2 Hz. Frequency of 10 raised to the power 2 Hz means 100 times in a second. and there must not be any human who can press the button of remote control 100 times in a single second. And so TRIAC is best suited on the ground of switching frequency here, as well as the device VI rating, as none of the home appliances is going to be greater than 1000 volt. Now let's see other points. TRIAC can withstand bipolar voltage. Isolator driver for TRIAC is easily available. It is easily available even in the case of BJT and power MOSFET. Zero crossing detection can be used to turn on. This point would be clear in coming up slides. And voltage control is possible for dimming of bulb, speed control of fan, etc. This point would also be clear in coming up slides. Now let's see the basic operation of TRIAC. What is a TRIAC basically? A TRIAC are like two anti-parallel SCR with a common gate. This is one SCR and this is other SCR, both having a common gate. Thus they are able to switch both sides of an AC sine wave. Hence this is bipolar device. Thus this is bipolar. They are able to switch both sides of an AC sine wave. Bipolar. Now a TRIAC switch controls the current through a load because it can be controlled to trigger at different voltage point on the sine wave. This point would be clear in the next slide as we see the waveform, how it is triggered at different voltage point on a sine wave. It can be used, therefore, as it can be triggered at different voltage point on the sine wave, it can be used to effectively control the RMS power delivered to the load rather than just turn on and off. Hence, this makes us clear about our last point, that voltage control is possible for dimming of bulb, speed control of fan, etc. Here it can be triggered at different voltage point on a sine wave and thus can be effectively control the RMS power delivered to the load. Now let's see the waveform, how we are controlling a different basic operation of TRIAC. And this is the waveform of the TRIAC, how it is triggered at different voltage point on the sine wave. Here in blue color is VG, that is gate, that is the voltage applied across the gate, VG. This is VG. In purple color is the source or a supply voltage. This is a supply voltage here, VS. In green color is the load voltage, that is a voltage across the load. This is V load. This is V load here, voltage across the load. And in red color is the current through the load. Here we are considering a resistive load. A load is resistive here. In red color is the current through the load. Now let's study the waveform now. This is the two anti-parallel SCR model of the TRIAC with a common gate. When, as we know, SCR is turned on when a gate signal is applied with positive anode cathode voltage across the SCR. Here in this case, suppose this be the VS here, VS be applied in this polarity, Vs is applied in this polarity. So when the gate signal is applied at this point here, this SCR turn on and start conducting, thereby making a supply voltage equal to a load voltage. And when at this point, when the load voltage, when a supplied voltage becomes 0 and start decreasing below 0, the current also decreases. The current also decreases below the point called holding current, and thereby the SCR turn off. Thus now no current is flowing through the SCR. And again, when gate signal is applied at this point, when a gate is applied at this point, a positive voltage is appearing across this thyristor. Thereby turning on this SCR, and the current start flowing in this direction till the value of the current reaches 0. At this point, when the value of the current becomes 0 and even falls below the holding current, this SCR turn off, and now no SCR is conducting, thereby there is no current through the load and a voltage drop across the load is 0. And this process continues, and thus the triac operate. Now it is like a switch that can turn on and off at different times on a sine wave, as I had said earlier. Is this only what we need to do? Of course not. This is not what we need to do. Then what we want to do with the triac? We simply want to switch on and off AC load. This is how we are going to do so. Here we apply a gate pulse at positive and negative zero crossing, so that here we are applying Vs is like that. Let's see here, apply Vs like this. This is our Vs, plus minus Vs, and when we apply Vg at positive zero crossing here, if we apply Vg at positive zero crossing here, this thyristor would start to conduct, thereby the load voltage follow source voltage till this point, when the current decreases below the holding current. And now this thyristor turn off at this point, and again a negative zero crossing starts with a gate pulse. This is the gate pulse which is given at negative zero crossing here. This is given here, and this turn on this SCR, and this SCR start to conduct in this direction, thereby making the load voltage again follow the source voltage. Here the load voltage again follow the source voltage. This process continues till we want our AC load to remain turned on, and whenever we want our load to get turned off, we just simply stop applying this gate pulse at positive and negative zero crossing, like here. Here we are not applying gate pulse. Here we are not applying gate pulse. And the load remains turned off. And whenever again, if we want our load to turn on, then we just apply a gate pulse here and our load would get turned on. Here, if we want to turn it on, we apply a gate pulse and our load would start from here. Our load would start again. So this is what we want. How we generate this VG? How can we generate this VG? This was not generated by our Arduino. This can be generated by using an IC named MOC3041, the same IC that was used for isolation of TRIAC with Arduino, that is power circuit from Arduino generates this VG. It would be made clear in coming up slides. And the thing that I had told earlier, that is zero crossing, I think that must be clear now. I had told earlier that zero crossing detection can be used to turn on, and I think this must be clear to you now that we are using here zero crossing detection to turn on our power load. Now, what is the difference between last waveform and this one? Let's see the last waveform and it would be clear to us. This is our last waveform. Here we are giving gate pulse not at positive and negative zero crossing but at some delay, that is delay angle alpha. And we are not stopping to give a gate pulse anywhere. We are giving gate pulse continuously after fixed duration, that is this is the fixed duration. After this duration we are giving gate pulse again and again. This thereby control the RMS value of the load control, and this principle can be used for dimming of bulb, fan, etc., as I had said earlier. Now it's a time to start with isolation between Arduino and power circuit. The zero crossing family of optically isolated TRIAC driver is an inexpensive, simple and effective solution for interface application between low current DC control circuit such as logic gates and microprocessor and an AC power load. Why we should use zero crossing family of optically isolated TRIAC driver? The first reason is this device provide sufficient gate trigger current. What is gate trigger? I had said here, this is gate trigger. This is gate trigger. This is provided by MOC3041. For high current, high voltage TRIAC, while provide a guaranteed 7.5 kV dielectric withstand voltage between power line and the control circuitry. An integrated zero crossing switch on the detector chip eliminates current surge and the resulting electromagnetic interference, EMI, and reliability problem for many applications. Thus, the high transient immunity of 5000 volts per microsecond combined with the feature of low coupling capacitance, high isolation resistance, and up to 800 volt specified DRM rating qualify this TRIAC driver family as the ideal link between a sensitive control circuit and the AC power system environment. This is the reason that we use optically isolated TRIAC driver. But how? How we can use opto-isolator are used in the case of track. MOC304 series IC are used. I had given the hint of this earlier. This is the figure of MOC3041 IC that I am using in my project, and this is the schematic of the same. I will be explaining the schematic later on. How the zero crossing optically isolated track driver works. Here is the schematic, the full schematic. The detector chip is a complex monolithic IC. This is a complex monolithic IC. This whole is a complex monolithic IC which contains two infrared sensitive inverse parallel high voltage SCRs which function as a light sensitive track. Here are two SCR. This is one SCR and this is other SCR. Two SCR which function as a light sensitive track, and this function as a light sensitive track. Gates of the individual SCR. Here is the gate of first SCR. Let's change the color. Here is the gate of first SCR that is connected to the zero crossing detection circuit, and here the gate of second SCR is also connected to the zero crossing detection circuit. This ensures that with a continuous forward current through the LED, when a continuous forward current flows through the LED, the detector will not switch to the conducting state until the applied AC voltage passes through a point near zero. The detector here would not switch. This means the voltage would not appear across both of these points until and unless we have IFT flowing through the LED and voltage passes through a point near zero. Let's simplify it. Here is the simplified figure of the same. Two things are needed: a forward current flow through the LED. This generates infrared radiation which triggers the detector, and zero crossing detection circuit ensures that the detector will not switch to the conducting state until the applied AC voltage passes through a point near zero. Thus, this is the definition of MOC3041. This is how MOC3041 is working. Now let's see the electrical characteristics of track. Here, this is the electrical characteristic of track. Here is the electrical characteristic. The detector or the track may be triggered on in the following ways. There are many ways on which a track can be triggered. First one is the LED trigger current IFT. This is the desired way. This is the way on which we want our track to get turned on. Other ways are exceeding the forward blocking voltage between two main terminals MT1 and MT2. This is also unwanted, and the most unwanted one is voltage ramp, that is transient, noise, etc., which are common in AC power lines, may trigger the detector accidentally if they exceed the static dU by dt rating of our track. This is unwanted and are most common. They normally occur whenever we are connecting an inductive load to our track. This occurs. So we must take a step to prevent this. Accidental triggering of main track is more likely. Occurrence, thus a form of suppression network commonly called a snubber must be used to prevent false turn on of main track. Thus, to prevent this we are using a snubber. To prevent this we are using a snubber circuit. A snubber circuit is used to prevent accidental turn on due to the exceed of static dU by dt rating. Now let's see the basic switching circuit with track, driver and load. Here is our track driver, here is power track, and here is our load RL. What is the function of each and every component over here? We already know the function of MOC, that is track driver, and track R. This resistance R in combination with RC stubber network prevent possible destruction of track driver in the application where the load is highly inductive. The gate resistor RG, this is only necessary when the internal gate impedance of the track or the SCR is very high. These devices display very poor noise immunity and thermal stability without RG. But both of these resistance cost something. Use of gate resistor combined with the current limiting resistor R can result an unintended delay. This causes delay or phase shift between zero crossing point and the time the power track trigger. Thus, there is a limitation of using. Thus, we should be calculative. We must calculate this resistance very carefully. Now let's see the complete waveform from IFT to our AC output. Here it is. This was the signal generated by our Arduino. Here user pressed the button 1 was pressed by the user, and here again the button 1 was pressed by the user. This was the duration. This was the signal generated in any input output pin of Arduino. This was the signal generated in the input output pin of Arduino. Now this signal was converted into this gate pulse by MOC 3041. And this gate pulse was used by track as the gate signal, and track generated. Both of these were used by track. Even this and this was used by track to generate this IAC, and track generated this, the waveform that we need. Here during this duration our AC load was turned on, and during this duration our AC load was turned off, and we get our desired result. Now we need, as I had said earlier, we need to protect our track from high dV by dt, that is more than that as that of the rated dV by dt rating of track. So we build a snubber circuit for this. Therefore this is our snubber circuit RS and CS, and we must calculate the value of R and C. As we see here the graph, the voltage waveform with and without a snubber circuit. Without a snubber circuit, the voltage rises with a rapid peak here, and with a snubber this rises like this, green pen, like this. This is the voltage rise. This was not a peak. I think eraser is required. Pen. This is our rise. Here it is how to calculate. Here we know that the voltage applied is a sine wave, that is Vp sine omega t. Then dV by dt can be calculated, that is dV by dt is equal to Vp omega cos omega t. Then we calculate dV by dt max. dV by dt maximum is Vp omega. As we know, the maximum value of cos omega t is 1. Therefore, Vp omega is the maximum value of dV by dt is equal to, as we know, omega is equal to 2 pi f. This is equal to 2 pi f. Therefore, Vp into 2 pi f, we get the maximum value of dV by dt. Therefore, the frequency is equal to dV by dt divided by 2 Vp into 2 pi max. That is where dV by dt is the maximum value of state dV by dt specified by the manufacturer. This thing we get from the manufacturer. This is the data that we get from the manufacturer, and from here we get f is equal to 1 by 2 pi root under LC, and C is equal to 1 by 2 pi f square L. We know this, I think, from pretty basic from circuit courses. We can choose the inductor for convenience. Assuming the resistor is chosen for usual 30% overshoot, R is equal to root under L by C. Therefore, from this we can calculate the value of RC and CS. Now this is our load connection. This is how I connected. Here my wires came from Arduino. Here it is Arduino. All pin 2, pin 3 and pin 4 and ground came from Arduino through a 220 ohm resistance. I connected MOC3041, and then a resistance, that is current limiting resistance, is here. Then RG, R, and finally a track with a lamp. I have not used a snubber here, as I was just using a lamp, not an inductive load at all. It was not inductive, the inductance was quite low, so I think not to use a snubber circuit. If you want, you can use it. Now it's a time for a little demo. Let's see it. This was a power electronic circuit that we made. This is a power electronic circuit, and here is an AC load, a bulb. Let's see it work on real time. Here the bulb turning on and off on the instruction from a remote control that is in my hand. Here it is the triac. This is triac, and the white color is MOC3041 on my breadboard. Here this is MOC3041, this is triac, and here it is Arduino. I think the vision is not too clear. Thank you friends for watching my video. I really admire your involvement in my work, and if you really liked my work and want to give some credit to me, you can just log on to my website www.wirelessarduino.co.nf. and like my Facebook page. You can even follow me on Google Plus or add any comment you think appropriate. You can share this website on your Google Plus page by using this button, or you can share it on your Facebook page with your friends or any group that you have joined, or you can even tweet this website on your Twitter page. Thank you once again. Goodbye, friends.